degree in Computer Science and Engineering from IIT Kanpur. Please give a big round of applause.
Thank you. Here I am once again back at the dais, but this time with a different objective. I want to tell you very briefly about the quantum technology and how in India we are trying to harness it under the National Quantum Mission. So I'm sure many of you would have heard about or read about this quantum phenomenon, quantum computers, and how they are going to change the world in many ways. So some of you may even feel curious about this. So I am hoping that I will demystify a little bit for all of you. Next slide. Okay, the quantum mechanics or quantum phenomenon as we know it has been around for 100 years. In fact, this is the year of centenary of quantum phenomenon. It was essentially primarily discovered in the year 1925 when Professor Heisenberg came up with his explanation of the uncertainty principle. But when it comes to quantum computing, which is what we are going to talk about today, apart from a few other things, that started from the statement by Richard Feynman, a very famous physicist, in 1981. When the computers were available by that time, very plentiful, and many physicists were trying to simulate their physical phenomenon through computers, and they were not succeeding very well because at certain levels there is this quantum mechanical effect that start taking place or start becoming important, and simulating the impact of those effects through computers was turning out to be a huge challenge. And that's when Richard Feynman made this statement that actually, the nature is quantum. And in trying to capture the nature through this classical computer, as we call it, is not going to work. So we need actually a quantum computer to simulate nature. So that was just an idle thought at the time, but it got people thinking about it seriously. And in last about 44 years, there has been a lot of progress in this direction. So let's see in what way does the quantum phenomenon start creating problems for normal computers. Next slide. Okay, so this slide shows on the left a bit. Now a bit is the most basic element of a computer. It stores one of two numbers, either 0 or 1. And in a bit you will either have, and depending on what you store, either 0 or 1, it will be there, you can change it, you can perform computations on it, and so on. But when we look at the corresponding, when we or rather introduce quantum phenomenon here, the analogous entity in the quantum world is called a qubit. That's present on your right. A qubit can have infinitely many different states. And these states are a linear combinations of 0 and 1 values. And so, in effect, a qubit, although it just it's like analogous to 1 bit, but the information that it can store is significantly more than the information a bit can store, which is just 0 and 1. So that's the first place where the power of quantum phenomenon becomes apparent, because now in the same space we can store a lot more information. Next slide. The next important impact of the quantum phenomenon comes through what we call superposition. On the left, you see a qubit, which, as I mentioned, is a linear combination of 0 and 1, and that's what is indicated on the top. If you see that equation, psi equals, there is this funny looking half angular bracket around 0 and 1. That is just to, it's a technical way of representing the fact that it is a angular bracket 0 means the value is 0, angular bracket 1 means the value is 1. And there are coefficients A and B, which basically are the coefficients of linear combination, with the property that you can think of A as cos theta by 2 and B as e to the I phi sin theta by 2, so which makes both A and B complex numbers. At least B a complex number, you may have A as still a real number. So this provides, and I already mentioned, a qubit to have a lot more information than actually. This is not the second power, it's the first power, which I'm repeating myself here. The superposition is what allows a lot more information to be stored on a computer, on a qubit. Next slide, that's when we come to the entanglement. Yes, that's the next power of a quantum computer, that we can take two qubits. Each one has a superposition of zeros and ones, and there is a phenomenon called entanglement, where we can connect these two qubits in a way that their value of one completely determines the value of the other. And then, no matter how far you take away these two qubits, this phenomenon stays the same. That is, you measure one, it gives you immediately the value of the other. Next. So, this two phenomenon, which is entanglement and interference, these allow for the power of the quantum computer to, or rather I should say the way of storing and processing information through quantum mechanical ways, which gives the power to the methods using, or gives power to the nature to do a lot more computation than a normal computer can do. There is no classical analogy of this, and that's why it's the original motivation of Feynman that if we can build a quantum computer, we can realize this as well. Next slide. So that gives the motivation of building a quantum computer. The question is, how does one do it? So in 1981 already there was a thought that let's try to build a quantum computer, but there were a huge number of challenges. As this slide shows, in order to build a quantum computer, you need a large number of qubits. Now today's computers have billions of qubits on which they operate. So you need a very large number of qubits to properly use a quantum computer. You need to be able to initialize those qubits, and you need to be ability to manipulate those qubits. Now there is unfortunately a phenomenon called decoherence. When you start manipulating qubits, after some time, they lose the value that is stored in them. It gets messed up. If the values get messed up, then of course there is no point in doing anything else. You have a query? Yes. I cannot hear you. strange quarks. No, quarks cannot be, at least till date they haven't been used as qubits. Photons, yes. Electrons, yes. But quarks, manipulating quarks, very, very challenging. So that's why they are not been. Although in principle they can be, but they haven't been. So I was saying about decoherence. So once you start manipulating this value stored in qubits, after some time the value is lost. So that you need to do your computation by the time the values, even before the value is lost. So that's called a decoherence time. How much time do you have available before the values get messed up? And decoherence time therefore needs to be large enough in order to do some respectable computation. And finally, measuring the value stored in these qubits. Because this is again, in the quantum world, even measurement is not so easy. So we need a good way of measuring the value. Now, in order to achieve all that, what one needs, typically, at least till today, is a setup where the temperature is brought down close to absolute zero. Some of you would be familiar with absolute zero, that is minus 273 degrees centigrade. So the temperature has to be very close to minus 273 degrees centigrade in order to do or achieve all of this. And that's what you see on the picture on the left is what we call a dilution refrigerator, which reduces the temperature to very, very, very small, very low value, and then the computations can be done. Next slide. Okay, now we have to manipulate the quantum. As I said, you store qubits, then you have to manipulate. Well, it turns out there are two special kind of gates. In the normal computer, there are AND and OR gates. Here there are some rotation and Hadamard gates. I'll not go into details now, but they can be constructed and you can manipulate the information. Next slide. So, what do? Well, you have, like in normal computer, you have an algorithm or a program running, which in a similar way, in a quantum computer, you have a program running, which will be realized in the sequence of these two gate operations. An example is given here. Next slide. So, that's the principle of a quantum computer. And Feynman says, well, nature is quantum, so one should have a quantum computer to simulate nature, but that's all nice to know. But the question remained, is there a specific, very hard to solve problem on a normal computer that can be solved fast by a quantum computer? That question remained open for 13 years, until in 1994, a scientist, Peter Shor, devised an algorithm that runs on a quantum computer, and it runs very fast, which can factor integers. Now, factoring integers, everybody knows what integers are or numbers are. All of you know that every number can be uniquely decomposed as a product of prime numbers. So the question here is, given a number, find all its prime factors. Now this problem is something you all would have solved in the school. You are given, let's say, 14. You try dividing by 2, 3, 4, and then one of the numbers divides it, that gives you a factor. But you start with a very large number, this method is not going to give you a factor quickly. And just to give you an example, there is a number written there on the screen. It's a single number, written in 1, 2, 3, 4, 5, 7, 8, 9, 10 lines. And the question is, find a factor of this, all prime factors of this. The number is so large that, even doing a single division on this is going to be quite nightmarish. So you can imagine finding factors of this number can take enormous amount of time, and indeed it does. If you try to even write a program on a normal computer, try to run the program to factor this integer, it's just going to take forever.
2048 जो है वो इस बड़े नंबर का फैक्टर है.
On the other hand, as Peter Shore showed, that if we had a quantum computer available, then this number can be factored very quickly. So that gives a very concrete and simple problem for which quantum computers are very useful. Now this problem is particularly of importance because the fact that you cannot factor large integers quickly, this property is used in securing our communication, day-to-day communication. For example, all of you use WhatsApp. There is WhatsApp advertises itself as end-to-end encryption. That is, nobody can read in between the message that you sent over WhatsApp. That's one of the main selling points, that nobody can eavesdrop. And the way that happens uses such large integers to encode your conversation. And the reason others cannot eavesdrop is because they cannot factor very large integers. So just imagine if one day when we have quantum computers available to factor such large integers, the WhatsApp communication, which we think today is very secure, will no longer be. Even worse, when you do online transaction, you make UPI payments or you go to internet, log into your bank account, transfer money. All that is secured through a mechanism like this. So all those mechanisms will also fail. And so doing any online transaction, whether it is through your bank or making a payment, they will all become insecure. So suddenly the world will change as we know it today. We are all used to working with our phones or computers and doing a lot of things online. None of that would be possible. Next slide. That's Peter Shore. I already described what he did and why it is important. Next slide. Okay, soon after, within a couple of years, this time an person of Indian origin, Love Grover, he discovered another very interesting algorithm on quantum computers. Normally, suppose you are given a set of 1 lakh numbers, okay, and it's jumbled up, it's not ordered, and you are asked to find out if 105 occurs in this set. How will you do it? You'll start searching first number, just check each number if 105 occurs, and you run through that set and deduce if 105 is present there or not. So the number of times you have to check if 105 is present, it will be about 1 lakh until you run out of the set. What Love Grover did was discover an algorithm which again can run on a quantum computer, which can do the same check, not by check, but we can run the same test, not by doing 1 lakh checks, but square root of 1 lakh checks. Square root of 1 lakh is, okay, so let's say 10 lakhs. If there were originally 10 lakh numbers, square root of that is 1000. So by just doing 1000 checks, you can actually determine whether the number occurs there or not. This is of incredible utility in all, let's say, internet searches. Today we do to go to Google and do a search for a particular item. Now that Google has a repository of just about all information spread over the world, and the Google algorithm actually performs a search in that to find what you want. with this algorithm, if quantum computers were available, the Google can perform the same search much faster. So, this is another, within a couple of years, 96, this was another very important discovery made. And since then, the need for building a quantum computer became even more desirable. That is, we really want to build quantum computers because this is extremely important. Next slide. Well, another way quantum computers are useful, and this is the original Feynman motivation, that the nature is quantum. So when you want to say, see how a chemical reaction goes, you run it on a quantum computer, so it will behave exactly like the nature, and then you can simulate, find it out much more quickly. Next slide. Now, over the last 5 odd years, this quest for quantum computers is becoming more and more intense. And every month these days, we find a new advancement. And here are some examples of this. Very recently, Microsoft announced that they have created a new method of building quantum computers, which has a lot of promise. As of today, IBM holds the record of building the largest quantum computer, which is 156 qubit. Still very small compared to classical computers, which will have billions of qubits. It's still only 156. But that's a good progress because 5 years ago we had 10, 20 qubit quantum computers only. Google is claiming some breakthrough, and all big companies are investing heavily, all major countries are investing heavily into building quantum computers. And India also announced a quest to build our own quantum computer 2 years ago through National Quantum Mission. Next slide. The National Quantum Mission was launched formally last year, 2024. It is being conducted by Department of Science and Technology. The Secretary, Department of Science and Technology will be here tomorrow, so you can ask questions about National Quantum Mission to him. Next slide. In the National Quantum Mission, of course, there are 4 different domains in which work is to be carried out. One is, of course, build a quantum computer. The target is to build a 1,000 qubit quantum computer over the next 5 years. Not only that, also discover new algorithms which can work very well on quantum computers. But the mission is not limited